Hello all. So this is the last session of module 3. In this session I'll be talking about ensemble methods, what is ensemble learning and what are the different types of ensemble methods like bagging and boosting. So ensemble learning is a powerful supervised learning technique that improves the model's performance by combining predictions from multiple individual models. And there are several types of ensemble methods and we'll be covering all of these today. So first we'll be talking about voting, which is also known as averaging. Then we'll move on to bootstrap aggregation or bagging. We'll look at a popular bagging algorithm, which is random forest. After that we will explore boosting, and finally we will cover stacked generalization, which is also known as blending. So first let us talk about voting, which is a straightforward ensemble method. It's essentially about combining multiple models' predictions. For regression problems, we simply average the predictions from all our models to get the final result. For classification problems, it is often a majority vote. As you can see in the diagram, we have three different models, a KNN, a decision tree and a logistic regression. So for a given data point, the KNN and logistic regression models predicts 1, while the decision tree is predicting 0 and the majority vote is 1, so the final prediction is 1. The individual weak models don't have to be perfect, but by combining them, we can get a much more reliable result. Next is bootstrap aggregation or bagging. So this is a meta algorithm which is designed to improve the accuracy and stability of machine learning models. The main goal of bagging is to decrease variance and helps to avoid overfitting. So here is how it works. We take multiple random samples of our input data with replacement. For each of these new smaller data sets, we train a separate model. Then a bagging classifier combines the predictions from all these models. And bagging is a special case of model averaging approach. So it is commonly applied to decision tree methods, which brings us to our next topic, that is random forest. So this is a very popular and powerful ensemble method. A random forest works by building multiple decision trees, and the random part comes from two places. First, each tree is trained on a different random subset of training data. Second, when a tree is built, it only considers a random subset of features at each split point. By combining the predictions of all of these different trees, usually by taking the average for regression or a majority vote for classification, a random forest can make a much more accurate and robust prediction than any single tree on its own. Next is the second major type of ensemble method, which is boosting. And the goal of boosting is to build a strong classifier by combining a number of weak classifiers in a sequential manner. So the process is like this. We start by building a model on the initial training data. Next, we build a second model that focuses on correcting the errors made by the first model. So that is done by giving more weight to the data points that the first model misclassified. And this procedure is repeated with each new model learning to correct the mistakes of its predecessors. And this will continue until either the complete training set is predicted correctly or we reach a predefined maximum number of models. So boosting is incredibly effective for improving the model's performance, especially on complex data sets. So this diagram helps visualize the boosting process. In the first step, our classifier tries to predict the input data. As you can see, some data points are misclassified. In the second step, we create a weighted data set where the misclassified points now have a higher weight. And the next classifier is then trained on this reweighted data, forcing it to pay more attention to the difficult data points. And this process will continue sequentially, and the final ensemble classifier is a weighted combination of all the individual classifiers, with each one contributing based on its performance. And the result is a highly accurate and powerful model. Next is stacked generalization, which is also known as blending or stacking. So this is an advanced ensemble technique. In the more traditional ensemble methods like voting, where we have multiple classifiers and we combine their outputs using a simple rule like majority voting or averaging. So stacking takes this a step further. Instead of a simple combining rule, it uses another machine learning model, which we call as a meta model, to figure out the best way to combine the outputs of the initial model. And this diagram is showing the stacking process. We start with our initial input data. We then train a set of base classifiers, which are often called level 0 classifiers. In this example, we are having a decision tree, a ridge regression, and a lasso regression. So all these things we have already discussed in the previous sessions. So each of these level 0 classifiers produces its own set of predictions. And the key step in stacking is to use these predictions as the training data for a new classifier, which is also known as a level 1 meta model. So this meta model learns how to best combine the predictions from the base models to produce the final optimal prediction. And it essentially learns the relationships and patterns in the predictions of the base models, making for a much more sophisticated combination than simple voting or averaging. Now let us move into some more detailed explanation of random forest, how it is going to work. We have just seen what is random forest. Now let us see how the algorithm of random forest is going to work. So it is a widely used machine learning algorithm because of its powerful performance and flexibility. And it is a fantastic example of ensemble learning method. It builds multiple decision trees and then combines them to get a much more accurate and robust prediction than any single tree could on its own. So a key reason for its popularity is its ease of use and its ability to handle both the classification and regression problems with high efficiency. So next is the steps in random forest algorithm. So first, to build our forest, we create multiple decision trees, and this process has two key elements of randomness. We take a random sample of our training data with replacement, and that is known as bootstrapping. So we do this for each tree. So every tree is trained on a slightly different version of the data. And at each node in a tree, instead of considering all the input variables, we select only a random subset of variables to find out the best split. And this helps to decorrelate the trees, making the ensemble more powerful. So after we built our forest, we can make predictions. For a new data point, we feed it through every single tree in our forest, and each tree will give its own prediction. And then we simply take the majority vote among all the trees to get our final classification. So this diagram shows the overall process of training a random forest. As you can see, we start with our main training set. From this, we are creating multiple training data subsets labeled here as 1, 2 and all the way to n. So these are our bootstrap samples. And each subset is used to train a separate decision tree. Once all these trees are built, we use them to predict on our test set. And we gather all the predictions from all the trees and then uses voting or averaging to get our final single prediction. Now this is a great visual on how the final prediction is made. So imagine we are having a new data point represented by the instance at the top. So we feed this instance down through all the decision trees in our forest. So this is a fruit classification example. So each tree gives its own prediction. So in this example, tree 1 and tree 2 is predicting class A, which is the apple class, while tree N is predicting the class B, that is banana class. So to get the final result, we perform a majority voting of all the tree predictions. So since most of our trees are predicting class A, our final output is going to be class A, that is the apple class. Now these are the some of the disadvantages and advantages of random forest algorithm. So on the advantages side, it is known for its higher accuracy and efficiency even on very large data sets, and it also takes less training time compared to some other complex algorithms, and it can handle missing data well without a significant loss in accuracy. And at the same time, it is having some disadvantages also. For regression, it cannot predict values beyond the range of training data, and the models can also become very large and slow to evaluate because they are made up of so many individual trees. And the biggest drawback for some applications is that random forests are considered as a black box. So they are very hard to interpret. So you can't easily see how they arrived at a specific prediction. So that can be a problem in fields where model explainability is very crucial. So next concept is about boosting. So these are the different types of boosting algorithms. First we are having ADA boost, which stands for adaptive boosting, and this algorithm assigns weights to the individual training examples and adjusts them based on the performance of each weak learner, forcing the model to focus on the points it gets wrong. And next is gradient boosting, which is a widely used algorithm that builds an ensemble of decision trees, and it works by sequentially adding predictors that corrects the errors of the previous models. And as even more advanced version is XGBoost or extreme gradient boosting. So this is an optimized, highly efficient version of gradient boosting that includes regularization to prevent overfitting. And finally, light GBM or light gradient boosting machine. So this is a high performance algorithm that is known for its speed and efficiency, especially with larger data sets. So we'll be seeing in detail about ADA boost and gradient boosting. So AdaBoost builds a series of models sequentially. The key is that each new model, say model 2, it is built to correct the weaknesses of the previous model, that is model 1. And this is a continuous process where each new model is trained to fix the mistakes of all its predecessors. And the predictions from all these models are then combined with more accurate models having a greater influence on the final output. So to really understand how this works, let us take a simple example. So we begin with the training data set. For our first weak learner, we are assigning an equal weight to every single data point. So here we are having 5 data points. So each one is given a weight of 1 by 5 or 0.2. And now for step 2, so here I have not mentioned as step 2, but already I have done it in the previous slide. So we are training our first weak learner often a simple decision tree called a decision stump on our data, and this stump will try to make a prediction. Then for step 3, we are calculating the amount of say, which is represented by the Greek letter alpha. So this value measures how much influence our weak learner will have on the final prediction. So formulas are already given there. We're just substituting the values. And the formula for alpha is based on the total error of the weak learner. As you can see from the calculation, the total error here is 0.2. That we have done in the previous slide. So when we plug this into the formula, we are getting an alpha value of 0.69. So a lower error rate results in a higher alpha, meaning the model is given more influence. Now here you can see a graph which gives you an intuitive understanding of the relationship between the error rate and the alpha value. So as the error rate is decreasing on the x-axis, the alpha or amount of say on the y-axis increases exponentially. So this shows that if a weak learner makes very few mistakes, it will have a very high influence on the final prediction. If it makes a lot of mistakes, its influence will be much lower. So now that we have our alpha, we can go to step 4, updating the sample weights. So the key idea here is to increase the weights of the data points that are first model misclassified. And the new sample weight is calculated using this particular formula. So for the data points that were correctly predicted, we use a negative alpha, which makes their new weight smaller. For the data points that were incorrectly predicted, we use a positive alpha, which makes their new weight larger. So in our example, the data point on row 4, it was slightly misclassified. So its weight has been increased from 0.2 to 0.3988, while the others have been decreased. Now for step 5, we normalize these new weights so that they add up to 1. And after normalization, you can see that the misclassified data point now has a much higher weight, that is 0.4982 compared to other data points. So we then create buckets for these normalized weights. And in step 6, we use these new weighted buckets to create the training data for the next week learner. So we randomly sample from these buckets. So there is a much higher chance of selecting the data points that were misclassified, and this forces the next model to focus on the difficult to predict examples. And this entire process, from calculating alpha to updating weights and resampling, it is repeated for a set of number of iterations or until the model achieves a desired level of accuracy, and then the final classifier is a weighted sum of all of the weak learners. So you just have to understand the process of AdaBoost classification algorithm. Problems from the sessions will not be asked much. You need to know the concept. So the next one is gradient boosting. So AdaBoost, it focuses on reweighting the data points, but gradient boosting is a bit different. It builds the models sequentially to specifically optimize the loss function of the previous learner. So the idea is that each new model or base learner is generated to be more effective at correcting the errors of the one before it. And gradient boosting is having three main components. One is a loss function. So that measures the loss function will measure the error of our predictions. And the goal of the algorithm is to minimize the loss function. And a weak learner, typically it is a decision tree that makes the predictions and helps form our strong final model, and an additive model which will combine the predictions from all the weak learners. Now this is a high level overview of the steps in gradient boosting. So we'll walk through each of these in detail using a practical example of predicting home prices. So first we will create a simple base model, like taking the average of all the target values. Then we will recalculate the we'll calculate the residuals, which are the errors between our average prediction and the actual values. The next we will create a new model that learns to predict these residuals, and we'll use these models predictions to calculate a new improved target value. And finally we will repeat this entire process, creating a new model that learns on the new residuals until our model is as accurate as we want it to be. So here you can see, so this process is illustrated here in this. So here under this slide you can see a trick, which is A greater than R greater than RM greater than R greater than RM, etc. So this is a great way to remember this process, that is actual values gives us the residuals which we train a new residual model on, and that gives us new residuals, and again it goes on like that. Now here is a small example using gradient boosting. So our goal is to predict the home price. So we start with a simple base model, which is just the average of all the actual home prices in our data set. As you can see, the average home price is 108. So for our base model, the default or average predicted value for every house is 108. And the next is for step 2, we will calculate the residuals. A residual is simply the difference between actual home price and our predicted average. So for the first house, the residual is 130 minus 108, which gives us 22. So we do this for every house and gets a new column of residuals. Now in case of step 3, we take the residuals we just calculated and treat them as our new target variable. a new target variable. And the goal of our next model, which we will call as RM1, that is residual model 1, it is to learn how to predict these residuals using the original features like square feet and number of rooms. So in this table, our model RM1, it makes its own predicted value of residuals. So our model is learning the patterns in the errors, which is the core idea of gradient boosting here. Now this brings us to step 4. We can now calculate a new predicted value for our home prices. And the formula is simple. We take our initial average predicted value and add the predicted residuals from our model RM1. And you can see this in the table on the right. For the first house, we take our original prediction of 108 and add the predicted residual of 25 to get a new predicted home price of 111. So this is a much better prediction than our initial guess of 108. Now next is uh, we are going to build our first residual model RM1 to predict that error, and this process is repeated with a series of new models RM2 and RM3 and so on. So with each one focusing on the remaining errors, and the final output will be a combination of all these models, and the formula shows that it's the output of the base model plus the predictions of each residual model, often with a learning rate represented by eta to control how much each model contributes. So this allows the model to learn in small controlled steps, and that will lead us to step 5. So now that we are having a new predicted home price, we need to find our new residuals. So we simply subtract our new predictions from the actual home price. So you can see the new set of residuals, and this process starts all over again. We build a second residual model RM2 to fit on these new residuals as our target, and this continues for a set number of estimators or until the residual error becomes very small. So at which point our model is as accurate as it can be. So this is the overall process of gradient boosting. So here also you won't don't expect any numericals from gradient boosting, just you have to understand the concept, how it is going to work. So that's all about the ensemble methods. So with this we have completed all the topics in module 3. That's all. Thank you.